Welcome back to another episode of Basement Physics. In this episode, we're going to take a few minutes and look at the concept of instantaneous velocity. If you remember in the last episode, we drew a few graphs when an object had a constant velocity, and from those graphs we were able to deduce the object's average velocity. In the previous episode, we plotted out a position versus time graph, and that produced a straight line if the object had constant velocity, and that straight line slope equaled the velocity of that object. Well, in this graph, it's also a position versus time graph, we have a slope, but it's not a constant slope. It's a changing slope over time. And so a question arises, what is the velocity at point A? What would be the velocity at point B and at point C? Well, let's give that velocity a name. Since we're looking at a velocity, that is a velocity at an instant in time, right there at point A, all of these points have what are called instantaneous velocity. To figure out the instantaneous velocity at point A, I'm just going to click on my pen here. I'm going to use the idea of the tangent. If I take my pen and I draw a line that is tangent to the slope of the graph, and I draw a right triangle, this line represents my change in time. This represents my change in position or change in displacement, and that would give me my instantaneous velocity would represent this slope. And if you notice, this is a positive slope, so for position A, one way you could describe the velocity is it is a positive velocity. If I go over to point C, I can use the same concept. I will draw a line tangent to point C. If I again draw the horizontal and vertical components of that line, this line will represent my change in position. This line will represent my change in time. And notice that this is position initial and this is position final down here. So this slope would be negative. This slope is positive. This slope would be negative. And if this slope is negative, the instantaneous velocity at point C could be described as a negative velocity. And now what about point B? Well, if I draw a line tangent to point B, I have a horizontal component, I have a time component, but I do not have a vertical component to that line. I do not have a change in position. And if I do not have a change in position, there is no change in displacement. And if there's no change in displacement, the velocity could be described as unchanging or zero velocity. So once again, a positive velocity, zero velocity, a negative velocity, and since I picked particular points, those could all be described as instantaneous velocities. Another question comes up, and I'm just going to pick a different color. Let's go purple. What is the average velocity from point A to point C? And if I draw the slope from point A to point C, let's just think about this for a minute. Velocity average. I got to think here for a minute. That's just change in position over change in time. Even though the object has moved its displacement and it has come back, notice that its change in position from A to B is zero. The change in time is roughly 4.8 minus 1.2. And that's in seconds, but the change in position is 0 meters. And so the velocity average from point A to point B is 0 meters per second. What a lot of students want to do is they want to figure out the velocity here and the velocity here, add them together and divide by 2, and use that to figure out the average velocity. But this statement always holds true to figure out the average velocity of an object. It doesn't matter if the object has a constant motion or if it has a changing motion, like this graph here. And I'd like to point out one other thing about this graph. If an object does not have, if an object does have changing motion or changing velocity, one thing you need to think right away is something is causing that change. And that something that is always causing the change is a force. We'll encounter that idea a little bit more in Chapter 3. I hope this helps.